All right. Draw a free body diagram for an object which is falling faster than its terminal speed. In this case, what I want is that the relative scale of the vectors is correct. As always in drawing free body diagrams, let's start with gravity because it's a non-contact force and it's embarrassing to leave it out. And now we know that the drag force, right, which we're at terminal speed greater than. So if we remember here, we'll have that the terminal speed is derived by saying it's the drag speed equal to the weight if your velocity is your terminal speed. So if the drag force was to be more than the weight, you must be going faster than your terminal speed. So we should have a terminal drag force which looks something like this. All right, because remember that 1/2 times CD times rho times A times V terminal squared, that by definition is the weight. If V is bigger than where I am, if B is bigger than the terminal velocity, then 1/2 CD, sorry, this is a bit messy. Remember that the terminal velocity is such that 1/2 the coefficient of drag times the density times the area times the terminal velocity squared is the weight. All right, but if we have FV greater than that, then the drag force is 1/2 C times rho times A times V squared, and clearly this is bigger than this, which means that this is bigger than that. So we have that the drag force is greater than the weight. That gave us, as we had before, just to show it quickly again, that we have some weight pulling downward and some drag force pulling upward. But wait, if the drag force exceeds the gravitational force, then the acceleration would actually be this way. So even though we have that the object is moving this way at a v greater than terminal v, then we still have that the acceleration is against that, which means, of course, that since A and V are opposed, the object gets slower. Instead of getting faster, the object gets slower because the acceleration opposes the velocity. Of course, once the object gets slower, then V has become smaller, so the drag force has become smaller, so the acceleration, while remaining upward, becomes smaller. But the acceleration being upward while the object falls downward means that it gets slower. And we have sort of the opposite of the reasoning we had before about terminal speed. And once again, we have that the object tends towards the terminal speed. At the terminal speed, of course, there'll be imbalance and there'll be no more acceleration. So either way, basically, we end up at that speed. That's why it's called the terminal speed. It's the speed to which the object will end up if nothing else interferes from outside. This basic concept is how a parachute functions. When you have somebody who's falling through the air, they'll have some relatively large terminal velocity, and that's bad news. Then they deploy a parachute, the parachute gives them much greater cross-sectional area, so that the terminal velocity becomes smaller. And the hope, of course, is that you reduce the terminal velocity to a speed at which you can safely impact the ground. For people, this can be from going from 120 miles an hour to only a handful of miles an hour. if you deploy a large enough parachute. By the way, it also is how drag breakers work, where they fire a parachute behind. In this case, there's no gravitational force pulling them forward, so there's just the retarding force. And so they coast to a stop in a much shorter distance because there's a much greater force on them. As a reminder, the terminal speed is the square root of 2 mg over the coefficient of drag times the density times the area. We'll try this problem. Falling without a parachute, Fergus has a terminal speed of 44 meters per second. That's about 110 miles an hour. A safe landing speed is about 2 meters per second. Fergus deploys a parachute and lands safely. Find the ratio of the parachute's cross-sectional area to Fergus's cross-sectional area. Well, we could take the ratio of their speeds. So we could take, I'm going to switch to the screen. We could take the terminal speed at the start, which remember was 2 mg over CD rho A, square rooted. And we could say, well, Fergus then has, after the chute deploys, I'll put a little star here. And it's going to be 2 mg CD rho, but now A star, the new area. And then we could see that algebraically we could divide one by the other. Why do we do that? As a general rule, if you want to change one thing and only one thing and see how some other thing changes, setting up the equation and then dividing, so we haven't changed the physical situation, just the values, will cancel out everything we don't care about. So here I'll end up with Vt over Vt star, in other words, his original terminal velocity over his new terminal velocity. And then I'll have, and I look at this and I say, well, 1, root over root is still a root, so we'll just have a square root going here. And then I say, hey, look, I'll have 2 over 2, that'll go away. I'll have m over m, that'll go away. G over g will go away. The coefficient of drag, we assume, doesn't change. And the density of air doesn't change. And so I'm left with just 1 over his original area over 1 over his new area. That's kind of messy, so I do a little bit of manipulation. And the way I divide fractions is to keep, change, flip. So I'll have square root. I keep 1 over his original area. I then flip. Right, I change the multiplication, and I flip to having his new area over 1, which any sane person would probably write as new area over original area. Remember, that's not actually really what we wanted. We are given, here is giving us the ratio of the terminal speeds, and we want this, so we need to solve over, and we want to say square both sides. So Vt over Vt star squared equals A star over A. So the thing that we want, well, the thing we want actually is A star over A, the ratio of their areas, and it's going to be the ratio of 44 meters per second to 2 meters per second squared, or 22 squared, which turns out to be somewhat more than 400. 484. His new area is nearly 500 times his original area, which, if you think about people parachuting, that's actually not that crazy. It's about 20 times the thickness. Yeah, that seems not crazy for a parachute. All right, as sort of a really extreme application of all of this stuff, we're going to watch somebody free fall from orbit. So this guy took this ridiculously complicated balloon, essentially. It's a weather balloon, more or less. And it's going to carry him in that capsule up to the edge of space.
Release.
If you're scared, walk away, 'cause there's
There's no need to feel ashamed. Yeah, we all feel the same. Whoa, where's your passion? Where's your fire today?
Alright, now the hole really looking now.
There he is at the edge of space, high enough to show a curve. And now he's just going to step out.
Jumper away. Speed 725.
You're showing Felix in a stable descent.
And then he plays parachute because otherwise this would be bad news.
And Felix is back to run safely, the new world record holder.
Anyway, so what we get there is just the guy jumps off from outer space. You can hear at least once he's moving at 725 meters per second, which is far in excess of the speed of sound. At the speed of sound at sea level, it's different up there, but still moving probably faster than anybody without an engine has ever moved before. So. Okay, the next two slides are entirely cultural. They're worth talking about. They're not a thing you have to do. I want to be really careful. There's a really scary looking equation on this page. You are not in any way responsible for this equation. It's largely there just because I got the number at one point and wanted to record it for people, and we want to see what it looks like on the next page. Here I've made an assumption that I can just take this constant k is just a shorthand for all of this stuff that doesn't change as the problem goes on. You get a bunch of exponential functions, so they're all of the form e to the something like t square root mgk in the power of the exponent. It's not unusual in math things to see this difference in sum of exponentials. Don't worry about all of that stuff. Don't worry. Here's the terminal velocity, which is interesting. That comes in. If you look at it, that will turn out to be what we had as our terminal speed. And so this is from a thing called Wolfram Alpha, which does all the calculus for us. The calculus is not fun. Don't worry about the math, but I'm going to plot what it looks like on the next page. And these are what the graphs of velocity and acceleration look like. So the axis is actually only, of course, really good for the speed. And I guess for the other axis, this is the plot of A versus G. So we see at the start, we end up with acceleration almost equal to G. And then it comes down, and as we get closer to the terminal speed, the acceleration gets closer to 0, as we expect. We see that the velocity starts off at 0, rises pretty rapidly, but then turns over and eventually gets closer and closer, but never quite gets to equal to the terminal speed, which is a feature of any of these exponential models, that they're really limit cases rather than actual cases. In real life, of course, if your speed differs by 3 protons per second, then people are going to say that that's essentially being at constant speed. So they're both in terms of sort of their base values, a over g or v over vt. I guess I could write that a little more clearly here. Is what the green axis is. The thing I wanted to point out, or at least want to look at, that's kind of interesting is the velocity is nice and smooth. It's what we call monotonic. I guess they're both monotonic, but it has just one simple exponential curve. But the acceleration kind of rolls over twice. All right, there's a point where it's the acceleration is changing faster and faster, then it changes at a constant rate, and then it changes the other way until it gets to 0. But this rollover I found very counterintuitive and unusual. I wasn't expecting it. That we start off at G, and we stay at G for a little bit before it starts to plumb. Not at G, but near G, until it starts to plumb down. There's a link to the Desmos file if you wanted to play with the calculation yourself. But mostly I want you to come away with the exponential curve for the velocity. That's really important. And that the sort of quasi-exponential curve for the acceleration, but having that little rollover. When they've asked this on the test, actually, they've never worried about that, which is interesting because it's such a relatively subtle thing. But it's interesting that the acceleration doesn't just fall off like an exponential, but has this little rollover. I want to remind you, the equations that generate these are not required, and while the general shape is required, the details are not required.